All right, folks, let's go ahead and get started then. So what I want to review today is some of the material from last night's video, and then let's build on that by talking about a new type of electron configuration or orbital diagram called the core configuration or diagram. So quick review. If we want to actually look at where the electrons are going into orbitals, one way we can do that is by way of what we call the electron configuration. All right, so for example, we'll just take the simplest element, hydrogen. The way we can do that is to recognize that hydrogen has a single electron associated with it. Okay, so we put the symbol for hydrogen there, which is the capital H. And then what I'm going to do is I'm going to write the lowest energy orbital, which is the 1s. Okay, oh, Siri thinks I'm talking to her. No, I'm not talking to Siri. All right, so we have a 1s orbital there. And we're going to put one electron into it because we only have one electron to work with. So we show that as a 1s superscript 1. Okay, so that's an electron configuration. And we can continue to add electrons to that orbital and then to subsequent orbitals as we go as needed, as we showed in the video. And we'll do more of that today as well. The other option we had in the video was what we called the orbital diagram. And I think Chem 101 calls it something else. We'll see that in a little bit when we get into Chem 101. And in the case of the orbital diagram, we do essentially the same thing. But now what I do is I actually show the orbital as essentially a blank line here. And I can put the orbital designation up underneath of it. But now what I'm going to do is I'm going to show the actual electron inhabiting the orbital. Now remember, I can only put 2 electrons into a single orbital. So the 1s electron can hold 2. One obviously would be spin up and the other would be spin down if I went all the way to helium. So usually we go in spin up first, spin down second. You don't have to do it that way, but as long as you end up with, by pairing, 2 electrons in their spin paired. All right, so that's your orbital diagram. And again, what it lets us do is it actually lets us see in a little bit more resolution how we're actually filling those individual orbitals in terms of electrons either being spin up or spin down. All right. Now, the next one we're going to deal with is going to be the core. Now, the core configuration can either be done as an electron configuration or as an orbital diagram. But what we're going to do here is we're going to actually differentiate between 2 types of electrons. We're going to talk about the core electrons, which are the electrons up to and including the configuration for noble gas. Those are the inert gases over on the very far right of the periodic table. And then we're going to have the valence electrons, which we're going to look at separately. And then those are any electrons beyond the core configuration, which is made up of the electron configuration of the noble gas. So we're always looking at the next previous noble gas to whatever species we're looking at. Okay, so let's just look at oxygen as an example here. Okay, so if I have oxygen, and we did oxygen, I think, in the video. Oxygen is going to have a total of 8 electrons associated with it. So let's just do this as an electron configuration. All right, so if we do the whole configuration, it's going to look like this. It's going to be a 1s2. Then after that, we go to the 2s. That's going to be 2. And then we still have 4 more electrons to deal with, and they go into a set of 2p orbitals. So that would be a 2p4. So if we add all those up, that should give us our 8 electrons. Now, here's the deal. With the core configuration, what we're going to do is we're going to look back to the previous noble gas associated with oxygen. And that's going to be helium. Now, helium has a full 1s orbital. We can also say that it has a full principal energy level, right? Because the n equals 1 energy level has been filled. Okay, so we're going to actually just represent that in brackets as helium. And then we're going to put the rest of the configuration out to the right like we normally would. Okay, so you can sort of see that as we move to heavier elements, this is something of a shortcut, okay? So that's the nice thing about this. If I get up to something beyond helium in the periodic table, well, we don't have to put all those core electrons in there. So again, any of the electrons associated with the previous noble gas are considered to be the core electrons. And then anything beyond the previous noble gas are considered to be the valence electrons. Now, valence electrons are the outermost electrons. beyond a full principal energy level. So in this case, it's every electron beyond the n equals 1 principal energy level. Now, valence electrons become important to us later on down the road when we start talking about bonding, because those are the kinds of electrons that take part in the bonding process. So this idea of being able to generate a core configuration becomes very important to us. All right, so we're going to continue to do this as we go. We're going to practice these so you can see how they work. So the next question we have to address, though, is that in the video, we really only went up through what? The second row of the periodic table. I think we showed the orbitals in terms of filling up through that part of it. And that takes us up. So what if we did this? I think I actually showed this in the diagram, or rather showed this diagram. If I had the energy of the orbital, I had a 1s here, and then I had a 2s, and then I had a set of 2p's that all light the same energy like this. I think I showed you that diagram in the video. And then what we said is we come back and we fill the electrons in as needed in this specific order. So we start with the 1s, we go to the 2s, and then finally we go to the 2p. And we talked about how we stick one electron into each 2p orbital and then come back and pair them as needed. Okay? But we didn't really go beyond that. So really what we need to know at this point is, well, what order do I fill the orbitals in? Okay, and the general rule is we're always going to go from lowest energy orbital to highest energy orbital, just like we did in the case of this diagram. Okay, so for example, if I wanted to do oxygen, I could show it here. There's 2, 3, 4, 5, 6, 7, and then we come back and pair to do 8. Okay, so that's how we would do oxygen. All right, so we'll just put O there for oxygen. But what if we wanted to go beyond that? We should be able to do this for any element in the periodic table. So the question is, once I get beyond the 2p orbitals, where do I go from there? Okay, so again, the general idea is I want to go from lowest energy orbitals to highest energy orbitals as required for the number of electrons that I've got in a given element or ion. Okay, so there's a few ways to do this. One way, and I call it sort of the high school method, is we can start out by looking at each principal energy level and then kind of build a diagram from there. So I'm going to just make my principal energy levels as many as I need to cover everybody in the periodic table. And we usually go up to about 8. All right, so what I have to do is I have to recognize, all right, what do I have in each one of these principal energy levels? Well, we know from our last time talking about this in class, I can build out orbitals depending upon what principal energy level I'm in. So remember, if I'm in the first principal energy level, the only orbital I have is a 1s. Okay, but if I go to the second principal energy level, remember what happens. I have a 2s, but then I build in a set of 2p's. So I would put 2p after that. Okay, so remember I have 3 of those, so I can put a total of 6 electrons in there. Now, if I go to n equals 3, I have a 3s, I have a set of 3p's. Oh, but then remember I get a new set of orbitals with each new principal energy level. So I get a set of 3d's. Now, if I go out here to n equals 4, I have a 4s, I have a set of 4p's, I have a set of 4d's, and then I pick up a set of 4f's, remember, because I'm going to a new principal energy level here. So now if I go to n equals 5, I have a 5s, I have a set of 5p's, I have a set of 5d's. I've got a set of 5f's as well. I also pick up a set of g's here, but I don't need g's, okay? They're there only if I need to go beyond the ground state, which means where I am before I promote an electron to some other energy level. Okay, so I don't really need to go past the 5f, so I'm going to leave it there. And then I can go to the 6s. I got a set of 6p's. Then I go to the 6d's, and I don't need to go to the 6f's or the 6g's because I won't need them. 7s's, 7p's, and then I have an 8s. So you get some, what I like to call sort of a sideways pyramid or Christmas tree here. So here's how this works. We're going to fill from top to bottom. So I'm going to start with the 1s, and I'll just show arrows to show you how this works. So 1s down to 2s. And then when I have to, I go across 2s to 2p. And then when I can't go across, I take a diagonal. So a 2p down to a 3s. Okay, so the trick is the diagonals. So watch what happens here. 3s, I have to go sideways to the 3p, but then I get a choice. I could either go from 3p to 3d, or I can go from a 3p down to a 4s. And here's how it works. I always take the diagonal when I can. So the 3p goes down to the 4s, but now what I have to remember is I have to come back to the 3d and pick those up. Okay, now I'm on a new diagonal, right? So I take the diagonal, 3d down to 4p, 4p down to 5s, and then I find my next diagonal. My next upwards diagonal is 4s. Where did I leave off? At the 4d. Okay, take my next diagonal, 4d down to 5p, 5p down to 6s. Now where do I go? Oh, I got to pick up the 4f's, don't I? So I'm going to bring a new one up to capture the 4f, and that starts a new diagonal, right? 4f down to 5d, 5d down to 6p, 6p to 7s. Then 7s should go all the way back up to the 5f, right? So the nice thing about this is, and then I go 5f to 6d, 6d to 7p, 7p to 8s, and that's pretty much all you need. So this basically shows you the order in which you're going to set these up. So you can kind of memorize this diagram, sketch it out on a periodic table that you have handy or whatever, but you can always use this. And it shows us the order in which to fill the orbitals. Now, I've got a better way to do it, but if you're comfortable with this way, it works just fine and you're welcome to use it. I'm guessing that probably half of you at least have seen it before, so it's probably familiar to you. Any questions about that before we start actually playing with it? And there's one other option I'm going to show you as well. Everybody sort of see how I made this? And again, something that's easy to reproduce. All right, so I'm going to leave this for just a second because the other way I can do this is I can use the periodic table. And you've seen this periodic table before. I used it, I think, somewhere else in the class. I don't remember when I used it, but it's useful. I went ahead and posted it up over at D2L under the announcements. So if you want to go get your own copy of it or view it from there, you're certainly welcome to do that. But basically, I'm going to run over to my files here, if I can find them. There it is, okay? So notice that I've got this nice color-coded periodic table. And the nice thing about this is this periodic table actually breaks up the different elements or regions of elements in the table according to what we call blocks. Okay, so you can see that the blue are the S block. And what that's suggesting here is that whenever you see that blue part, I'm putting S electrons into the atom. The P block is green, so every time you see the greens, you're putting P electrons into the atom. The Ds are sort of this nice pinkish color, and that's what we call the D block. So anytime you see that color, okay, you're putting D electrons in. And then these sort of orangey ones are the F block. You see those down there, and that's where we're actually putting F electrons in, okay? So the nice thing about this is you can really kind of tell, just based on where you are in the periodic table, exactly how to fill the orbitals. We just move in the sequence of the table, okay? So we would start with hydrogen, right? And in hydrogen, notice that if we're there, we're going to have a 1s electron. That's element number 1. So move across the table to helium, which is element number 2. And you're still in the S block there because you haven't filled that 1s yet. So another way of thinking about helium is it could kind of be over in the 2s region there, but it's a noble gas, so we kind of stick it over on the right. But it could be over in that gap over here where I have the S. So you could think of it as being there just as well. Okay, you go down to element 3, which is lithium. Okay, so what's it telling you to do? Well, notice that you're now in the 2s block. And notice below that you have the 3s, the 4s, the 5s, the 6s, and the 7s. So you're just working across. Okay, so you go from element 2 to 3. So lithium, okay, that tells you you're going to put its first electron into 2s orbital. Go to beryllium, you're putting that second electron into the 2s orbital. Where's element 5? Go all the way across. You'll find boron there. Oh, but now you're in the P block. Now notice which P block you're in, right? You're in the 2p block. Okay, so that means you're going to be putting 2p electrons in to get from boron through neon. Then where do you go after neon? Go down to element 11, that's sodium. You're back in the 3s. Magnesium takes you to filling the 3s, then across to the 3p. That takes you through argon. Then you go down to element 19, so you got potassium to calcium, that's your 4s. Now look what happens here as I go from element 20 to element 21. I go from calcium to scandium here. So notice what happens once I go through the 4s's. Now I start picking up d electrons because I'm in the d block. But now notice what d block we're in. It's the 3d block, okay? And that makes sense because where's the first principal energy level where you pick up a set of d orbitals? Oh yeah, it's n equals 3, isn't it? Okay, so be careful. You're not going from a 4s to a 4d. You're going from a 4s to a 3d. And then that takes you through zinc, zinc across to gallium. That takes you back to the 4p's. And it just continues on from there. Okay, the only other funky thing that sometimes happens is when you get down to barium, which is element 56 down here. Okay, you're finishing out a 6s, but notice what happens here. Lanthanum, which is element 57, actually puts an electron into the 5d. And then notice where we go after that. Element 58 actually starts your F block. So cerium would actually be a what? A 4F1, okay? And then when you get to element 71, lutetium, where do you go? You go back up to element 72, which is hafnium. So you go back and you start refilling the 5Ds. And then you go to the 6Ps and you get it from there. All right. Now, if you go back and look at the Christmas tree diagram that I showed you, it doesn't really show that. It shows that you fill the 4Fs before you do the 5Ds, and that's perfectly acceptable. So you can really show it either according to this, or you can go ahead and fill those 4Fs first and then come back and pick up all the 5Ds. I'm happy either way, okay? So let's actually take a look at how we might actually use this. By the way, any questions about this? To me, this is very intuitive and it's very pictorial, so I like it. And I don't have to actually reproduce any diagrams to show it. In the old days, back before I gave you this, people would just annotate a periodic table I gave them and put the blocks in there and then they could just use it. But this one's nice because it has them all for you already. All right, everybody see more or less how to work that? And again, I put this over at D2L for you guys, so you have your own copy of it you can go get over there. So let's actually mess around with this a little bit, and you can keep looking at this if you wish, but let's just try an example of one of these things here, okay? So let's do lead, for example. Do a heavy one, okay? Great big one with lots of electrons in it. So what I'm going to do is a full electron configuration for lead to show you all the different orbitals. And again, you can either use the Christmas tree here or you can use the periodic table. But let's see if we can just do a full electron configuration for lead. So again, we start at the top, lowest energy, and we start filling in sequentially from there. So obviously we start with the 1s. And by the way, lead has what, 82 electrons in it. I know that because that's its atomic number in the periodic table, and that's a neutral lead atom. Okay, so I start with a 1s2. I go from there to a 2s2, right? Then I go to the 2p6. So I always go from the 2s to the 2p. There it is in the Christmas tree diagram. 2p to the 3s. 2 electrons can go in there. Then I go to the 3p, right? So that would be a 3p6. And again, the nice thing about the periodic table version of this is you can kind of keep track of where you are without having to back calculate or back count the electrons there. So I go from a 3p6 down to a 4s2, right? Where's the 4s go? Goes to the 4p. So that would take me to a 4p6. Where do we go from the 4p down to the 5s, right? That can take 2. All right, and let's see, 5s needs to go back up to the 4d, doesn't it? All right, so that would take me to a 4d10.
I have a question.
Sure, go ahead.
So I noticed that you skipped 3D. Do we do that every time? Mm-hmm.
No, I shouldn't have skipped the 3D. Did I miss the 3D? I must have missed it because it should be in there. That's after the 4s, right?
Yes.
Thank you. It should be in there. That's a 3d10. Thank you. Did I get it right after that? 4p5s. Yep, that looks right. Thank you. 4d10 to a 5p, right? 6. And then down to a 6s2, right? I'm getting close, aren't I? Where does 6s2 put us on the periodic table? It's getting pretty darn close. Where do I go after the 6s2? All the way back up to the 4f, don't I? Yeah. And I'm just going to do them in blocks, so I'm not going to worry about putting that single 5D in there and then picking up the 4fs. You can certainly do that. I'm just going to fill the 4fs first. And we can put, what, 14 electrons in there because I have 7f orbitals. So that's a 4f, 14, and then I go from there to the 5D. That's a 5D10. I think I'm almost there, aren't I? And then from a 5D, where do I go after the 5D? I go to the 6p. So then how many electrons do I need in the 6p? I'm almost there at this point. I think I just need 2 in there, don't I? So it's a 6p2. And that, if you add them all up, should give you the 82 electrons back. Or if you're using the periodic table, you're just kind of keeping track as you go. And then when you hit lead, you know you're done. Okay? But let me show you here in terms of what the actual core configuration would look like. And we could do it as a core orbital diagram. So how would I do that? Well, let me just jump back to my periodic table real quick that I had here. Let's just find lead in it. Okay, here it is. So lead is over here, element 82. There it is. Okay, so if I want to do a core configuration or a core orbital diagram, what I want to do is go back and find the previous noble gas to lead. So what's the previous noble gas before lead? Just kind of work backwards till you find one. What's the previous noble gas before lead?
Xenon?
Xenon, you got it. So xenon looks like element 54, and that's where I have basically filled my 5p orbitals. Everybody see that? So I've got a full set of 5p's to get to xenon. So if I go back to this thing, 5p, let's find 5p. There it is. I'm just going to put a little divider here. Everything prior to that is xenon, isn't it? So xenon takes you up to a 5p6. Okay, so if I wanted to do, for example, a core orbital diagram, I would put xenon in there, and that takes me all the way up to the 5p6, doesn't it? And then where do I go after that? I go to the 6s2, but now since I want to do an electron configuration, I'll make that a 6s. You put an electron in, spin up, spin down. Then I go to the 4f14, so I need, what, 7 of those. And that's what, the 4f's? So now I fill them in, spin up, spin up, spin up, 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 and then I come back and put the electrons in paired. Then I go to the 5d10, right? So I need 5 of those because that's how many sets of d orbitals I've got. Same thing. Spin up, spin up, spin up. I think I only have 4 there. I need a 5th one. Spin up. Down, 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 down. And then I go to the 6p2, right? So how many different p orbitals do I have? I have 3 of them, a px, a py, and a pz, and that's going to be my 6p's. I only need 2 electrons in there, don't I? Okay, so I'm going to go spin up, spin up. Okay, because remember, those 6p's all lie at the same energy, so I distribute before I pair. All right, so that's what the core orbital diagram would look like for lead. All right, so again, we can get a little practice doing that. So see how I found the previous noble gas, and then I just put that in brackets, and then I took everything past that. So that's a whole lot faster than actually having to take all of those different electrons in terms of the configuration prior to xenon or up to xenon. Okay, so it saves us a lot of time. All right, so that's the nice thing about a core configuration. All right, another thing that's worth mentioning here, and that is, let's talk a little bit about ions. So what if I had, and I'll just do electron configurations here. What if I had F1 minus? Okay, so that's the fluoride ion. How would I do, for example, a we'll do an orbital diagram for it, core orbital diagram. How many electrons would that have? So again, let's go back to my periodic table here. Okay, find fluorine. It's element number 9, right? There it is. Okay, so a regular old fluorine atom would have 9 electrons, but what if I had an F1 minus, a fluoride ion? How many electrons would that have? So how many electrons would be an F1 minus? Okay, you got 9 in a regular fluorine atom. So how many would you have in an F1 minus?
10.
10, very good. Okay, so we can have anions, which mean we have to add extra electrons, or cations where we have to lose them. Okay, so in this case, we're adding one. Okay, so fluoride, would have 10 electrons. Okay, what was the previous noble gas to fluorine? Oh, it's a row 2, so it's helium. We'll just do it as a core here. So that takes care of the 1s. So now I have a 2s, and then I have the 3 2p's, which is where I'm putting those extra electrons. So the helium accounts for 2 electrons, doesn't it? So now I need 10 total. So I have 8 more to go. So that's 1, 2, 3, 4, 5, 6, 7. Now come back 8, 9, and 10. Okay, so that's what I would have for the fluoride ion. Okay, what if I had calcium 2+? So let's go back and look at calcium in the periodic table here. Where's my files? There we are. Where's calcium? Okay, calcium is over there. That's element number 20, isn't it? Okay, so let's say I wanted to have calcium 2+. Okay, if regular calcium has 20 electrons, how many electrons would I have to have for calcium 2+? What do you guys think? Regular calcium's 20 electrons, calcium 2+ would have how many? Easy math, guys. 18. Very good. You got to lose 2 electrons to get to the 2+. Very good. So I need 18 of them. Okay, so for calcium 2+, I'd need to have a total of 18 electrons. Now, in this case, I probably would end up doing a full configuration, wouldn't I, to do that? Because if I did a core configuration, what would calcium 2+ look like? If I were doing a core configuration, what would calcium 2+ look like? Would it look like a noble gas? Let's go back and look on the periodic table here. So if I lost those 2 electrons to go back to 18, what element would I look like?
Argon.
Argon, very good. Okay, so really, if you get right down to it, calcium 2+ is just an argon core, isn't it? So I could write it just quite simply as that. Okay, because I would have that extra 2 electrons that are in whatever s orbitals there that we were in, and you lose those, you're back to the argon core. Okay, so that kind of makes sense to everybody. So since we're here, there's just 2 other definitions I want to look at before we do a little practice. And that is, I want to just cover this idea of magnetic properties. And we could apply this to either atoms or ions, depending. Okay. And we have 2 definitions here. Outside of the normal ferromagnetic definition that we talk about, which is when we talk about a regular magnet, we have like iron filings or something like that, and they stick to a magnet. That's ferromagnetism. But in a simpler sense, we can have 2 other definitions. We can say that a species is either diamagnetic, or we can say that a species is paramagnetic. Okay, what does diamagnetic mean? Well, it means from a physical perspective that the atom interacts weakly with an external magnetic field. either weakly or not at all. Okay, so when I say an external magnetic field, I'm talking about the magnetic field provided by, say, a magnet, okay? Now, what do we look for when something's diamagnetic? Well, what we're looking for is no unpaired electrons. So all the electrons have to be paired up. All right. Paramagnetic is exactly the opposite. That's where the atom interacts strongly with an external magnetic field. And what are we looking for here? We're looking for one or more unpaired electrons. So the thing is if when I go back around and I start looking at, for example, orbital diagrams, I can predict the magnetic properties of a given element or ion by looking for either unpaired electrons or paired electrons. Okay, so if I go back up to these two examples right here, fluoride ion, do you see any unpaired electrons in there? No, all the electrons are paired up. So would you expect that to be paramagnetic or diamagnetic? That's this guy right here. It looks to me like it's going to be diamagnetic because I don't see any unpaired electrons. What about calcium ion, the calcium 2+ that we did here? Any unpaired electrons there? No, because you got full argon configuration, so everything's paired up. So I'd expect that one also to be diamagnetic. Go back up to your lead ion. Paramagnetic or diamagnetic?
Paramagnetic.
Very good. I see 2 unpaired p electrons there. So I would expect this guy to be paramagnetic. Very good. Okay, everybody see more or less how that works? All right. I think it's probably a good time to practice with a little bit of this stuff. So let me pop over to Chem 101 here a little bit. So I am going to run this over to my in-class exercises.
Can you share the paramagnetic definition again?
Sure will. I'll run it right on down. So it's basically that the atom interacts strongly with an external magnetic field. And how do we look for it? We see one or more unpaired electrons in there. Okay. So I think I'm going to actually go back and look at a couple of orbital and quantum number ones. So I'm going to start with the exercise that we didn't do on Friday because we ran out of time. And it says 15 minutes here, and we're not going to need that much time to do it. But this is probably not a bad idea to just take a look at a few of these things. And again, you can just pick a few here. Matter of fact, we can even do a few together if you want. So actually, I've got it open right now, but let me run over so we can kind of see it on our screen share here. Chem 101's over here. Got it on my other screen, but this way we can look at it together. Okay, and that is, here we go. Here we go. So, for example, let's look at number 2. It says if L is equal to 0, which of the following may be true? All right. And you guys are going at it here, and this is fine, but let's take a look at what we've got. So if we've got L equals 0, what is that telling me? It's telling me that I've got a p orbital, I'm sorry, an s orbital, doesn't it? So can we have n equals 6 and have an s orbital? Sure we can, right? Now, what's m sub L? That's that magnetic quantum number, isn't it? Now, if L is equal 0, can I have an m sub L equal to a -1? No, I can't. Can I have an m sub L equal to 1? No, I can't. It has to be 0, right? What about m sub s? That's the spin quantum number. Can it have a value of 1? No, it can only be a half or minus a half. So it looks like the only real option I've got is that n can equal to 6 because I'm in a 6 principal energy level. I can have an L equals 0 s orbital there. But none of those other quantum numbers, B, C, D, or E, work for an S-type orbital. Okay, so you can kind of see that the answer there is going to be A. So a lot of these problems just deal with sort of process of elimination like this. Like number 3 is probably good for that as well. So which of the following orbitals cannot exist? Okay, it looks like you guys have a 3F there. And I would actually say that would be correct because to get an F orbital, what principal energy level do we have to be in minimally? In other words, can you have F orbitals in the 3rd principal energy level? No, you only get S, P's, and D's there. You don't pick up F's till you get to the 4th principal energy level, right? So 4F would be good, a 5F would be good, 6F would be good, but you can't have a 3F. So you get the basic idea here. So I'll let you guys work some of these. And hey, if there are any questions about these that pop up you want to discuss real quick, just let me know. But you get kind of how this works. And while we're at it, because I know people are going to finish this one up real quick here, I am also going to open up the one with electron configurations and orbital diagrams, which is what we were discussing today. So once you finish this one up or get to the point where you're a little tired of it, pop over to the next one. Practice some your orbital diagrams and electron configurations. See how you guys are doing here. All right, so it looks like some of you guys are struggling with D. It says how many orbitals are allowed when in the subshell when L equals 2. When we say subshell, we're talking about a type of orbital here. So if L equals 2, what kind of orbital am I talking about? What type of orbital is an L equal 2? So remember, a 0 is an S, a 1 is a P. L equals 2 has to be what kind of orbital? A D, right? So if you have a set of d orbitals, how many orbitals are in a set of d orbitals? That's what they're asking you for based on that quantum number. Should be 5, right? So is that what we got? Yeah, that's correct. All right, let's see how we're doing with the electron configurations here. See if anybody's gotten over to that yet. A little more orbital stuff to do over there too. And by 3, you're getting into the stuff we were doing today. Some of these ask you about this thing called the ground state. That just means a regular electron configuration of an atom in its normal state. If you go to the excited state, that's when we're promoting an electron or electrons up to some higher energy orbitals. But ground state is when everything's kind of in the normal electron configuration that we talk about, just in case you're not familiar with that term. So any questions so far, guys? Any of these you want me to look at with you?
Is an electron with an upspin a negative or positive 1/2?
That would be a positive 1/2 in the upspin, negative 1/2 on the downspin.
Okay, thanks.
At least that's the way I've always done it. It's really kind of random. You really could assign it the other way if you wanted to. All right, guys, looks like I'm at about 12:50. So if there aren't any other questions, I'm going to head and log out. And just remember, keep up, new video for next time. And look for a 5 for 5 on Wednesday, guys. And remember, we get Friday off this go round, so you don't have a Friday quiz.